Now this next identity is also very important as we look forward in generating functions, but we are going to show that this is really true for all k and n. Now take note that we have here the ratio of 1 over 1 minus kx, and it's actually equal to the summation of all k to the power of n and x to the power of n, as n starts from 0 to positive infinity. How do we show that this is really true? Now we are going to anchor on the previously proven identity in the previous video, so please try to look into that, review that video as well. We have the identity there that the summation of x to the power of I, where I starts from 0 to positive infinity, is just equal to 1 over 1 minus x. Okay? This is true for all. We have proven this already. Now this is different because the numerical coefficient here is just equal to 1. But our given here is actually k, and it's true for all values of k. So how do we show using this relationship here? Now, since we're using I in this given previously proven notation, and here is n, if we're going to substitute that for n, this is how it will look like: x to the power of n, as n starts from 0 to positive infinity. Again, we have here 1 over 1 minus x. So as you can see, when we compare it with n, we have noticed a similar item that came out here. Now we're going to show that for this expansion, there exists k to the power of n, okay, that is multiplier for all elements before adding them into 1. So let's start with this method or illustration, or you can also call this as proof, but since I am just going to show that it's true, of course I can also try to use the proof for that. So we have here 1. I'm going to start with the left hand side and return to whatever be the right hand side is equivalent to. Okay, so with this, what if we let kx is equal to a certain variable which is r? Okay, so this is equal to 1 over 1 minus r, okay, which is actually equal to this form, which can be presented in this manner here. Okay, so the reason why I also presented the previous video, and of course in the previous video I also made some claims that the identity in the previous video will be used to prove also other identities. That is why we had this one here. So once we achieve 1 over 1 minus r, this is equivalent to this notation, but instead of x here, it will be formed into r. So you have here the summation of your r to the power of n here, notice, as n starts from 0 to positive infinity. And what is r again? R is actually kx. So this is equal to, this is equal to the summation of your r, which is just kx raised to n, as n starts from 0 to in positive infinity. By the use of power law, we can now say that is just equal to the summation of k power of n x to the power of n as n equal to 0 to positive infinity. That means from here we're able to arrive into that, proving this. So just for the finishing of this portion, so hence we're able to declare that 1 over 1 minus kx, that's kx, sorry, let me write it again, 1 minus kx is equal to the summation of k to the power of n x to the power of n as n starts from 0 to positive infinity. So you have proven this. So still, of course, if you would like to use proof, you may. So we were able to prove this identity using the previously discussed identity. That's why this is very critical and very important. So take out the proof from this side. We were able to denote this notation as r, leaving this matches the identity in the previous video. So we use this side. Instead of x, we will have r, and we return the value of r earlier as kx. Later on by power law, we reach our intended target. This means, this is its implication now. If you have this notation, if you have an example, 1 over 1 minus 2x, so the expansion here will matter on the value of k, because you have here k to the power of n. So you have 2 to the power of n, x to the power of n, as n starts from 0 to infinity. Okay. In short, 1 over 1 minus 2x is equal to 2 to the power of 0 x to the power of 0 plus 2 to the power of 1 x to the power of 1 plus 2 squared x squared plus until 2 to the power of n x to the power of n, which is actually just 1 plus 2x plus 4x squared plus dot 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 plus 2 to the n x to the power of n. this is the expansion for this, which is different just by expansion of the previously discussed identity is just equal to 1 plus x squared plus x cubed until you will have x to the power of n. It's very different. The coefficients are not longer equal to 1. So for this, the sequence is equivalent to 1, 2, 4. Probably the next one is 2 cubed 8, and then so on and so forth until 2 to the power of n. Okay? So this was actually 1, 1, 1, 1, so on and so forth. So this is the proof for that. It is an example expansion that we can use since we have already proven this given identity. Thank you very much for watching.